Now, this next bit is a bit embarrassing because I'm having a bit of a barney with my next door neighbour. You see, they think that the water coming from my pond is draining into their garden and their side of the hedge is growing faster than my side, so they have to cut it more often. And it's a bit embarrassing because I don't want it to come to a fight because she's 90 and, well. Oh, statistics. That could be the solution. So what I've done is I've taken 25 leaves from my side of the hedge and 25 leaves from her side of the hedge and taken at the same point, so they're the same age. The sun comes at such an angle that they both get the same duration and intensity of light, so that's not a factor. So I guess if there's a difference in the size of the leaves, that might indicate whether she's right or not. Well, the plot thickens. It's got a wee bit embarrassing, this, because what I've done is I've plotted a graph for each of the sets of leaves that you saw on the table. And as you can see, the two curves, which are both normally distributed, they're not exactly the same. And in fact, hers are a bit bigger than mine. But is that difference significant? What we need is a test. And this test is called the t-test. What it does is it compares the two means of the two samples, but it also looks at the degree of spread of the two samples. In other words, the standard deviation that we looked at in part 2. Now you're probably thinking this is pretty scary, but it doesn't have to be. Certainly not as scary as that. You just have to be very careful about applying the numbers to the formula. This will then allow you to calculate what is called a t-value. This t-value corresponds to a probability that the differences in the leaves is just due to normal variation, or alternatively, there is a significant difference. If we plot the graphs again, but this time with the standard deviation along the x-axis rather than the area of the leaves themselves, and then we slide the two graphs apart, when we get to this critical point, this is the point where we agree that there is a significant difference between the samples. In other words, a 5% or less overlap. This can all seem a bit confusing, so probably the best thing to do is to go back to the leaf data and to put those figures into the formula and then get our t-value. So how do we translate that t-value into a probability of overlap? Well, the first thing we do is to make a statement about what we think the result will be, what we call a hypothesis. But we frame it in negative terms, and we call it a null hypothesis, which says that there is no significant difference between the mean of my leaves and the mean of my neighbour's leaves. So how do we interpret this t-value? Well, we look it up in a set of t-tables. And as you can see from the tables, there are vertical columns and there are horizontal rows. The row we're interested in is known as the degree of freedom. And the one that we use is given by the formula n1 plus n2 minus 2, where n1 and n2 are the number of leaves in this case. So that'll be 25 plus 25 minus 2 is 48 degrees of freedom. If that's not available, you go to the next nearest one below. So that's the only row that we're interested in. We are going to ignore all the other numbers. What we do now is we take our t-value of 1.32 and we look across the table to see where that number fits along that red row. And we can see that it fits somewhere to the left of the number 1.684. That corresponds to the column above where it says p equals to 0.1. So therefore, the t-value corresponds to a probability of greater than 0.1. We write this like so. To give you some other examples, if the t-value had been 2.27, then this would have fallen between the probability of 0.05 and 0.02 and would have been written like this. Or if the t-value had been 4.6, then it would have fallen beyond the probability of 0.001 and would have been written like this. So at last we come to interpreting this p-value. And it can get a bit confusing, so I've tried to make it easy by calling it Rowley's LSD rule. And that is, if the t-value corresponds to a p-value which is less than 0.05, then there is a significant difference between the means of the two samples. And conversely, if the t-value corresponds to a p-value greater than 0.05, then there is no significant difference between the means of the two samples. So that means in the case of the hedge dispute, there was a t-value of 1.32, which corresponded to a p-value which was greater than 0.1, which says that there was no significant difference between the means of the least samples from my side of the hedge and my neighbour's side of the hedge. And so we accept the null hypothesis. Now I've got to go and tell her, I suppose.